It doesn't look real.
It is longer than many aircraft wings. This is one of the largest composite structures ever built. Almost everything that makes it work is hidden forever. The blade alone dwarfs the vessels sent to maintain it. Every curve has been engineered to control moving air. It bends by design, because rigid structures eventually fail. Hidden beneath the surface is a structural framework engineered to survive billions of loading cycles. Long before the first fiber is cut, the entire blade exists only as engineering data. Millions of calculations verify the design long before manufacturing begins.
Everything begins with materials that appear surprisingly ordinary.
Before a single component is assembled, thousands of individual composite pieces must first be shaped with extraordinary precision.
This enormous mold will determine the shape of every millimeter of the finished blade.
Every completed blade begins with one perfectly positioned layer.
Layer by layer, fiberglass, carbon reinforcement, and structural foam build the blade's internal strength.
And somehow, this unfinished structure will soon become one of the largest composite components ever placed into service.
Each new generation has become larger than the one before it.
Every additional meter increases the area that can harvest energy from the wind. As blades grow longer, the engineering challenge grows even faster.
It must be lighter than expected, stronger than steel in the right places, and survive decades of relentless offshore wind.
The answer begins with materials engineered for an entirely different purpose than steel. Each individual glass fiber is incredibly thin, but together they create remarkable strength. Carbon fiber is used only where extraordinary stiffness is absolutely essential. Each material performs one specific job. Together they become one extraordinary engineering structure. If built from steel alone, the blade would become too heavy to support itself.
Even a blade this large is designed to flex, distributing offshore wind loads with controlled precision. Before manufacturing begins, the blade has already survived years of virtual testing. Only after every calculation is complete does manufacturing finally begin. Before a single fiber is installed, every millimeter of the mold must be perfect.
An invisible release layer ensures the finished blade can eventually separate from the mold. The first reinforcement establishes the foundation for everything that follows.
Layer by layer, fiberglass, carbon reinforcement, and structural foam create a lightweight structure of extraordinary strength. These carbon fiber spar caps will carry the greatest structural loads throughout the blade's entire lifetime. Hidden deep inside the blade, vertical composite walls quietly carry extraordinary structural loads. The lightweight core separates the structural skins, creating remarkable stiffness while adding very little weight. Every composite layer is now in place, waiting for one remarkable engineering process. Before the resin can enter, almost every trace of air must first disappear. Slowly, liquid epoxy moves through the fiberglass, turning dry layers into one continuous composite structure. The blade is now one continuous composite structure, but it still has one crucial transformation ahead. Although the fibers are now fully saturated, the blade has not yet reached its final strength. Billions of microscopic chemical bonds permanently lock the entire composite structure together.
After hours of controlled curing, the blade finally emerges. The manufacturing process may be complete, but the engineering verification has only just begun. Even the smallest dimensional error can affect aerodynamic performance.
Instead of cutting the blade open, engineers inspect it using sound. Heat can reveal subtle structural differences hidden beneath the surface.
Only after every engineering requirement has been verified is the blade ready to leave the factory. Even after manufacturing, every movement remains carefully engineered.
Every support point has been calculated to minimize structural stress. Hundreds of independently controlled wheels work together as one machine. Transporting the blade requires engineering every bit as carefully as manufacturing it. The factory is only the beginning. The next challenge is reaching the open sea. The blade is never lifted from a single point. Every load is carefully distributed. Every lifting point is calculated long before the crane begins moving. This floating construction platform is one of the most specialized engineering vessels ever built. The ocean never stops moving, so the vessel simply lifts itself above it. Every movement is slow, deliberate, and calculated. Despite its enormous size, the final alignment is measured in millimeters. Thousands of engineering hours are secured by one final mechanical connection. For the first time, every engineered component works together as a single machine. Before entering service, every critical system must prove it performs exactly as expected. Every rotation quietly transforms offshore wind into clean electrical power. What began as digital engineering has become one of the largest machines humanity has ever placed into the sea. Building the blade is only half the challenge. Proving it meets every engineering requirement is equally important. A difference measured in millimeters can influence aerodynamic efficiency across the entire rotor. Instead of cutting the blade open, engineers inspect it using sound. Heat can reveal subtle structural differences hidden deep inside the composite structure. Every structure has its own acoustic signature, and even the smallest defect can change it. Every rotation transfers enormous forces through this single connection. The blade is only as strong as every bond hidden beneath its surface. Only after every inspection is complete can the blade begin its journey toward the sea. Long before the blade reaches the ocean, engineers have already simulated decades of operation. Even after installation, engineers continue learning from every rotation. Every blade is engineered to withstand years of wind, salt, rain, and constant fatigue. Every inspection protects millions of future rotations that have not yet happened. Only after every engineering requirement has been satisfied is the blade cleared for service. After months of engineering and manufacturing, the journey to the ocean finally begins.
Only a handful of facilities are capable of handling cargo of this scale. The engineering journey now leaves land behind.
Hundreds of kilometers from shore, precision engineering begins all over again. The ocean never stops moving, so the vessel simply lifts itself above it. Suspended beneath a heavy lift crane, the blade is guided upward with extraordinary precision toward the waiting rotor hub.
Despite its enormous size, the final alignment is measured in millimeters.
One by one, every connection is tightened to an exact engineered load. For the first time, every engineered component works together as a single machine. For the first time, every engineered component works together as a single machine. Every rotation quietly transforms offshore wind into clean electrical power.
One blade may seem extraordinary, but together they become an entirely new energy infrastructure.
What now appears effortless is the result of thousands of engineering decisions working together with remarkable precision. Behind every giant offshore wind turbine blade lies an extraordinary story of engineering, precision, and human ingenuity.